All right, day 17. We get a computer with a program. It has 3 registers and it has a set of instructions with an opcode and an operand. And then we should move through the instructions, taking 2 at a time, and depending on the opcode and the operand, we should perform different tasks, and so they are defined here. So we'll start by creating a struct for a instruction. It has an opcode. It has an operand. And then we can generate the new function for that. And then we have the program or the computer. It has 3 registers, so register A, B and C, and the list of instructions. So we'll start by creating the program from a string. Or we could create it from a file, actually. Even easier. So we create it from the input string. Need to grab the input as well. Oh, this is... So we need just to grab all of the numbers in this, so we can use regex. And we just want to capture digits. They will all be positive. Unwrap that. And then regex, iterate over the capture, which is data. And then we need to map each string to a number. We get back a capture, actually. And the actual capture is at index 0. And then we want to parse and unwrap that. And collect. So then we have a list of usize. We then want register A. So let register A, B, and C. And then instructions. And this is to get the rest, so we get the first 3 from the list. Is equal to data. We need to get it as a slice, so everything. Otherwise, we can panic. Because then the input data is corrupt. And can I do that? Yes. No, I can't. And then the instructions we need to map to instruction. So let instructions be instructions iterate no. We want to get it in chunks, so chunks by 2, and then map that chunk to a instruction. So then we have created the program. We now need to run it. So we'll create the solve function. It will take a mutable reference to self, and it will return. So we no longer this is the first day where we are not returning a string. Instead we are not returning a number, instead we are returning a string. So it's a set of numbers separated by comma. So it should return a string, or we can just print it when we get, so we can say it doesn't return anything. We'll just print the result. So we need to keep track of where we are in the instructions, because if we get the jump, which is this one, we can move in the program. So let index be 0, and then while let sum instruction be self instructions get I. So now we need to implement all of the rules. So first one is a division. It performs a division. So it should take the number that is in the A register, and then the denominator is found by raising 2 to the power of the combo operand. So we need to have a function to get the combo operand, and those rules are defined here. Dividing by 2 to the power of a number is the same as bit shifting it to the right. So let's get the combo operand. So the rules say if it's 0 to 3, we just return whatever it was, and 4, 5, 6 map to separate registers. So we can just match on the operand and then say for 4 we return register A, 5, 6, B, C, and otherwise we just return the operand. So on the instructions, we need a default where we can panic. We need to match, of course. I was looking here and then I was writing here. So map on the instruction opcode. Now I wanted that. So default fail. So if we have a 0, it's the A divide. Then self register A will be self register A bit divided by the combo. So let combo be the combo operand of the instruction operand. All right. 6 and 7 are very similar. It's just that we store it to register B or register C. If we have 1, then we do an XOR between the literal operand and store that to register B. And so the literal is actual operand without getting this combo operand. Number 2 is a modulus. It keeps only the lowest 3 bits. And that should be the combo modulus 8. 3 is the jump. And here we need to check if register A is 0. We should do nothing. Otherwise, we should jump to where the literal operand is. And we have to divide this by 2 because we store each instruction as an item. So if register A is not 0, then I will be equal to the literal divided by 2. And then we only have four and 5 left. So 4, that is also a XOR, but now we instead do it between register B and register C. And the final one, the output. This actually adds outputs the number, so we should print it. So we can create an array of the outputs, or a vector. So it should always output the combo operand modulo 8. And in the end, to create a string, we can join it. So output, iterate over it, map each number to a string, collect it, but we should collect it to a vec. And then we can join on comma. And so running this does nothing because we haven't actually run the program. So immutable program, new, solve it. Of course, we need to actually move forward in the program as well. And it should be +1, not +2, because we combine the two. And so then we get the correct output. Let's compare it just to be sure. Yes. And then for part 2, now it gets real interesting. So we should now ignore what is in register A, and instead we want to find the value of A that makes the program output itself. And we will start by just changing some things in the program. We want to keep track of the original B and C so we can reset. And we also want the expected output, that will be the instructions. So original B, original C, and expected. And so original B will be register B, C, C, and expected can just be the instructions here to back. Then in the solve function, we no longer want to print the output. Instead, we want to check how many outputs are as we expect. So we'll delete that one as well. And then we'll have a keep track of an output index instead. And so here in the outputs, instead of writing the output, we will still let the output be combo modulo 8. But now we want to check if the output is expected. And if it's not, we will just return, because then it's like if the first output we get is not 2, then we can just abort. There's no reason to keep checking the rest of them. So if self-expected get the open index is sum and expected should be equal to the output, then great, we can just keep searching. Otherwise, we can just return, and we can return the open index, because then we can keep track of how good it actually did. Then we have a special case, and that is if open index is actually bigger than the current, and it can happen that it outputs everything correctly, and then it just, but it's not done. It keeps outputting numbers afterwards, and that also needs to be a fail. So if the index is bigger than the expected, we'll also increase it by 1. And then we will return a usize. And in the end, we will return the output index. So now we can test this. So this should be 0 because this is not correct, right? And it does output 0. So So we now have a I'll just comment this out. So we can have a goal of how many correct we want, and that is the expected length. And then we can just search for potential A's. So let's do 1 million searches for register A. So we can say program register A is equal to A. Let result be program solve. And then if result is equal to goal, that means we have solved it all. So then we can print A, and then we can return. So we can run this, and we don't find the goal. So, like, let's say a billion then. Okay, it's running. Okay, maybe if we run it in release. Still running. So, and the actual answer is much bigger value than this. So we can't just completely brute force it. So I took a break when I got to this part because I didn't know how to solve it. And then I went about my day. And then I just kept thinking that this is just a bunch of like bitwise operators. Maybe there's a clue there. So maybe there's a pattern in how the bits must be for the register A. Right, we actually need to reset it also. And so reset. It should set self register B to or original B. C. It doesn't matter. So maybe there's a clue there. So let's say if we just wanted to find like so the first 3 was correct. Could we get a pattern there? So let's collect a list of potential A's. So we'll just say if result is bigger than 2, we will print the A. We don't need that yet. So, yeah. That was a bit too many. All right, so let's say 1,000,000. And then we could look for a pattern here. I can't really see a pattern. There probably is, but what if we printed the A's as binary instead? And when I print binary, I can say that I want to have at least 16 zeros. So 0, 16. Or is it 16, 0? No. Why have I forgotten how to print? Is it? I do 32. Okay, that looks better. So, is there a pattern here? And so, I can see that the third bit is a 1 on every one that has given the first 3 as a true. So maybe when we keep searching, we can just assume that the third bit is always 1. And also it seems that the second bit is always 0. So then we just need to count here and count here. So what we could do is take the number and just insert first a 0 at index 1 and then a 1 at index 2. So I have a playground here to show. So let's say we have a number which is like this. So this would be the potential A. We can create a so this will just be a 1 1 1 1 1, and then let's say we wanted to set the third, the bit at index 3 to 1. We can create a mask by bit shifting the T. So the first 3 will be 0 and the rest will be 1. And then the opposite mask will be the opposite. And so the higher bits will be out of this. It will be a 1 here, but this will be 0. And the lower bits, it will only get this. And so then if we do the higher bits, bit shifted 1 up, because we want to move in this one. And then we bit shift a 1 to the index. And then add the lower bits again. We will have inserted a 1 here. So the new result is 1, 1. And if we wanted to insert a 0, we would just delete this. So to test this, it's easy to do some mistakes, so we'll create some unit test. So test insert 1 at index. So let's say we have a number which is like this. Then we want to insert at index 2. This would be here. Then we can assert that the result should be a 1 there. And then the function we can call insert 1 at index. So the number and the index. Then we can create this function and create, no, it didn't want to. All right, that's fine. So number index and it should return AU size. So first we want to create the mask. For the index. And then the higher bits will be the number and the mask, and the lower bits would be and the anti-mask. And so then this will be the result, a copy from the playground. And so then if I run the tests, it passes. Great. We'll do same thing, but for 0. So then it's this one, and then we want to add a 0 here. Insert 0. It will be the same except we do not want to add a 1 there. And then it will be a 0. So we'll run the unit test for that, and that passes as well. So now we could and so now we can see that at index 1 we want a 0, and at index 2 we want a 1. So we can let A be insert 0 at index 1, and then let A be insert 1 at index 2. And so now we got more results because we didn't have to check as many. So maybe now we could find new result. Maybe we could look for bigger than 3 instead. Okay, not a lot. Now, it seems like if we get more than 3 outputs, even the first bit is always a 1. So then we could add this to the first one and then just run again. Maybe we can look for 5 or more now. Yeah, we didn't find anything there. Seems that like this bit is always set as well. But this is a lot of manual work, and we want to solve this automatically, of course. So what we'll do is that we'll save all of these potential A's to a, and maybe potential A's is a misleading title. But these are the A's that we have tried out. So if we get a good result, we'll add the potential the A to the potential A's. And in the end, we need to find all of these automatically. And so let's create a function that takes a bunch of numbers and returns all of the indexes that are always the same. And we'll create an enum for the bit if it's 1 or 0. And we'll add the partial EQ and EQ here also. So it will return a list of index, and if it's a 1 or a 0, that is the same. So create a result, and then we need to create the zeros by themselves. It's probably a more elegant way to do this, but this is how I do it. So for each index, we want to check if all are 1 for that index. So here for index 0, it should return true. So if numbers, iterate over them, all of them, and then we want to check if number and 1 to the bit index, if this is not 0. Then we want to add the bit index and a 1. And for zeros, it's the same thing. However, we get a bunch of leading zeros, like we get all of these, and they are misleading. We need to remove them. So I'll first add this to a list of the zeros only, and then I'll trim away all of the leading zeros. So I'll just do this in reverse. And if zeros get the first one, is sum and the value would be the bit index, then we will remove it. Otherwise we will break, because then it's no longer a leading 0. And then for each 0 in zeros, I'll add it to the result. And then we want to say that this is a 0. Then we need to sort it, because we always need to add the index 0 first and go from right to left. So sort by key. And return result. All right. So let's create a test case for this also. So let's create some numbers. And let's have them all end with 101. So this will have a... Right. So this should return 3. So result will be common bit indices numbers. Expected would be 0, 1. Zero, so 1, 0, 1. Assert equal expected result. Okay, so it needs to derive debug also. And it failed. So the leading 0 part obviously failed. So let's see where it went wrong. We need to reverse it first. All right. Obviously, this can be written a lot better, but it's not really the important thing here. So we've collected we should now be able to solve this. So here we can get the guaranteed bits to be the common bit indices for potential A's. And then we want to search again. And then we can search for a bigger find here. So let the guaranteed bits be a new list. And then for the minimum, and this will be what we are searching for. So we will start by 1, and then when we find a bunch of guaranteed bits, we'll set that they are always guaranteed, and then we will up the search until eventually need to not print so much also. Until eventually we should find the result. So if result is bigger than minimum, then we can add it to the potential A's. And we can do 1 million. We do that quickly. Now we no longer want to hard code this. Instead, we want to, we can shadow A, and then for every guaranteed bit, we can do a is equal to match on the bit, and then 1, insert 1 at index, and A is the number, index is the index, and the value of index. And the same for 0. And of course we want to iterate over this so we don't get memory issues. We initialize this, we get the result. We could maybe print here we found a bunch of guaranteed bits. Yeah, so we probably need to run this in release. And eventually we got the result. And that is the correct result, I think. We can copy the... It looks correct, right? So, when we only searched for 1, we couldn't find a pattern at all. But then we found 2 guaranteed bits. Then we found 8 guaranteed bits. 11, 12, and just eventually we found the correct A. So, yeah, pretty fun puzzle. I hope this will work for all inputs and not just mine, because it's not really deterministic. Well, it is, but yeah, it will probably work for your input as well. All right.